All right, everybody, welcome back. So we met line integrals with respect to arc length. And so now we're going to meet three other kind of line integrals. These are not with respect to arc length, but with respect to our three favorite variables, x, y, and z. So these turn out to be a little bit easier to handle since they don't have that arc length factor in the integrand that has that square root in it, right? So how does this work? So if our curve r of t is given by x of t, y of t, z of t, then those derivatives, x prime of t, y prime of t, and z prime of t, we can write like dx dt is x prime of t, so we can write dx is x prime of t dt, and similarly for dy and dz. And so the line integrals of some function, say f, along the curve C with respect to x, y, or z are then defined as follows. So the one with respect to x, which we write like this, is given by, say, the integral from a to b of f of x of t, y of t, z of t times x prime of t dt. This is this dx here. Note that r of t we could replace here, so we could write x of t, y of t, z of t is just the curve r of t. And the bounds here, a and b, are going to be the places where we cut off the curve. So there'll be the lower bound for t and the upper bound for t when we're looking at our curve r of t. And similarly, the line integral of f with respect to y along c is given by the integral from a to b of, again, f of r of t times now y prime of t dt. That gives us this dy. And last but not least, we have the same thing for z, where dz is replaced with z prime of t dt. And so as I said, we could just write for some shorthand, which might be helpful as we go along here and I'm running out of space on the slides or something like that. We could write f of x of t, y of t, z of t is just f of little r of t. Okay, and oftentimes they like to give us examples where they just combine a bunch of these at once. So they give us some function times dx plus some function times dy plus some other function times dz, and they ask us to just do it all at once. And that's completely doable, as we'll see in the next example. So for this example, we will let C be the straight line segment that joins the points 1, 0, 2 and 4, 1, 5. Now, we want to parameterize C. We want a function r of t, right, to give us this curve. Well, we remember from probably chapter 12, section 5, way back at the beginning of the term, how to find the parametric equation of a line that passes through some given point and points in the direction of some given vector. Well, this line, it looks like it passes through the point 1, 0, 2, and it goes in the direction of the displacement vector that goes from 1, 0, 2 to 4, 1, 5 in space. So that displacement vector is given by the difference here of respective components. So its first component is 4 minus 1, which is 3. Its second component is 1 minus 0, which is 1. And its last component is 5 minus 2, which is 3. So recall then that the equation, the parametric equation of the line that passes through the point 1, 0, 2 and goes in the direction of this displacement vector has the equation, or that line is given by 1 plus 3t in the first component. We'll have this point plus this guy times t. 0 plus 1t in the second component. And 2 plus 3t in the last component. So we could shorten that up here. Just forget the fact that there's 0 on the front of the y component there. Okay, and looks like when t is 0, we get 1, 0, 2. And when t is 1, we should get 4, 1, and 5. So that's exactly what we need to trace out the line segment that starts at 1, 0, 2 and ends at 4, 1, 5 and is a straight line between those 2 points. So now that we have that, let's look at some funny looking line integral over this curve. And it might be given in some bizarre looking way. So what do we have? All right, but if we're going to do that, though, we need to have these derivatives. So let's note that x prime of t is given by 3. That's the derivative of the x component with respect to t. Y prime of t is just 1, and z prime of t is 3 again. So, okay, now let's take a look at some funny-looking expression of a line integral over c with respect to maybe x, y, or z, or a combination of all three of those. So that would look like some kind of expression as follows. So this one, I just pulled these out of thin air here. This y squared, x, and xz. They're not informed by anything else in the problem. There's some new thing that you might be handed. So we still have this same curve here, c, which is that straight line segment, and we're asked to compute some line integral that looks as follows. How do we do this? We have y squared dx plus x dy plus xz dz. Well, the prescription here then, we can read off as follows. That we'll take the first function to be y squared. And we will do the line integral along c of y squared with respect to x. And then the second function we'll take as x. We'll do the line integral of x along c with respect to y. And then the last function we'll take as this one, x times z. We will do the line integral of x times z along c with respect to z. And then we'll just add these three together. And so in this example, I'm going to do each one separate and we'll add them together. But at the end, we'll be able to see how, if you're kind of clever with the way that you can order things on your paper, that you can really just end up doing it as just 1 at the end. So that's kind of fun. All these integrals we end up doing are with respect to actually t, the parameter for our curve. So let's watch that go here. So the first function was y squared. And our curve has y of t equals to just t. So that gives us t squared then, and x prime of t is 3. So we have here t squared times 3 dt for our first integral. And those parameters are 0 and 1 every time, because the way that we modeled our curve was that we let it start at t equals 0 and end at t equals 1. Okay, and so then the second function is just x, which we know from our curve is 1 plus 3t. And then y prime of t is just 1, so we have here 1 plus 3t times 1 dt. Okay, and then the last one here is x times z. And we know from our curve that x is 1 plus 3t, and z is 2 plus 3t. And then we have to multiply by z prime of t dt. So z prime of t was 3. So this last integral is maybe a little bit more dirty looking here. Okay, that's fine. Not so bad, though. So the first integral is just t cubed, right? We have 3t squared. It integrates to t cubed. And the second integral is just t plus 3/2 t squared. These are very routine, right? And this third one here, I'm going to yank the 3 out and then FOIL out the inside here. And so we have 3 times the integral from 0 to 1 of 2 plus 9t plus 9t squared. So we'll take care of that one in the next step. Let's evaluate these first two at 0 and 1 and take the difference. We get 1 for the first guy. And then we get here, for this one, I think we get 1 plus 3/2, which is 5/2. And then now let's take care of this last integral here. We have 3 on the outside times 2t plus 9/2 t squared plus 3t cubed. Very nice. So we can evaluate this guy at 0 and 1 and take the difference. And we'll have still 1 plus 5/2 left over from the first part. And then it's really this last expression here that we're evaluating at 0 and 1. And so what do we get? 3 outside times the quantity 2 plus 9/2 plus 3. And if we multiply through by 3, we get, let's see. Well, first we've combined here 1 and 5/2 gives us 7/2. And then 3 times 2 is 6. 3 times 9/2 is 27/2. And 3 times 3 is 9. And if we add all of these guys together, we get the number 32. So not so bad. It seems like maybe there's a tedious amount of individual pieces, but I think that you can get around that by just starting at your first step in consolidating everything into one integral as follows. You could just start by, you have 3t squared, and then you have plus 1 plus 3t, and then you have here plus 3 times the quantity 2 plus 9t plus 9t squared. That becomes 6 plus 27t plus 27t squared. If you want to simplify first, this becomes what? Something like 30t squared plus 30t plus 7. And you integrate just that one thing from 0 to 1, right? The bounds are the same on each one, and the variable's the same for each one. So you should just be able to get this in just one nice integral if you like. And I think that's probably the preferred way to do that. But since it's our first one, I tried to break it down into as many individual pieces as possible. All right, so these are pretty good. We're going to like these kind of line integrals a lot. So stick around for the next talk where we'll find out how to employ these so that we can take integrals of vector fields, a new concept. We'll see you then.